Hello. Next, we are going to discuss how can we solve learning to rank or ranking problems as they're called. This is a different type of machine learning problem, different from classification and regression. And here the objective is not to assign the class to a given example or regress it to a certain value. But what we want is, let's say, is to rank or produce a ranking order of different examples in a given training or test set. What that means essentially is, let's say, is this apple better than this other apple? So an example of that again is the US apple grading system, in which you have got some apples that are called US extra fancy apple, and you've got a US fancy apple, which is a slightly lower quality apple, and then you've got the lowest quality, the US utility apple. And you can, so let's say for a given apple, what we want over here is we want to classify what, or we want to determine where should I rank its quality. Now we can model it as a classification problem. You can have, let's say, a class for each of these categories that we have. But if we think a little bit, this is not exactly a class assignment problem. When we are trying to solve classification problems, we have distinct classes. Let's say we've got apples and we've got oranges, and there is no relationship between, like, an apple is greater than an orange or something like that. But here, for a given apple, or let's say if you've got two apples, there's an ordering between them, or there's a rank assignment between them. So, for example, this is greater than this one because it's of higher quality, and then this is greater than this one because this US fancy is higher than US number one, and so on. So there's an ordering, whereas if you take a corresponding multi-class classification problem in which you have apples, bananas, and oranges, and so on, there is no such order that a banana is greater than an apple or an apple is greater than an orange. So the difference there is the meaning or the existence of a ranking order. So perhaps if I want to predict what a given fruit is, I'll use a classification or I'll use a classifier. Whereas if I want to determine whether I would like a certain fruit whose picture is being given or not, or to what degree would I like that, then that makes it a ranking problem. So if you give a machine learning model an apple, because I like apples, you must have guessed that by now, that should produce a higher rank in comparison to either of the other two. Okay, so this is what is called learning to rank. Essentially, what we are trying to do is to assign a rank to an input example. Another example of learning to rank is from the medical domain, in which we have like cancer grading. So let's say if you take a sample from someone, a biopsy of someone, and then what pathologists do is that not only they tackle whether the person has cancer or not, or what type of cancer it is, but they also measure the grade of that cancer. So if the cancer is of higher grade, then that means that it has a certain set of patterns. Let's say if this is grade 3, this is nastier in comparison to grade 2 cancer, and then grade 2 cancer is nastier than not having or there isn't much cancer in there. Okay, so there is definitely a grading problem. Okay, so the prognosis decreases with the grade. So this is worse, actually, for a given patient. Grade 3 is worse than grade 2, and grade 2 is worse than grade 1. Again, we can model it as a classification problem, but we'd be missing out on that relationship. Just to emphasize that point, or to summarize that, I put it on this particular slide. Classification is the assignment of a given object into different classes. Typically, no semantic relationship between classes exists. That is, you cannot define greater than or less than in apples versus oranges versus mangoes versus bananas and so on. On the other hand, regression is the assignment of continuous values, for example, and they do have a relationship. Age, a person, let's say if you design a machine learning model in which you have, we give it a picture of a person. So this is a person, and you give that as input, and the machine learning model determines what the age of that person. Then two people, let's say one of them is 21 and the other is 18. There's a relationship between these two. 21 is greater than 18, so a relationship exists. But it's essentially a quantified or a quantification of this of the relationship. In ranking, what we are interested in is assigning ranks, which are qualitative rank assignment. So this is better than that, or this is worse than that. In the cancer example, we can say that grade 3 is worse than grade 2, which is worse than grade 1, right? Okay, so that's the main goal. Similarly, if you're doing quality assignment to apples, we can say that the best quality apple is this one and the lowest quality apple is then this one, but that is the relationship that exists between the two. Okay, so now what we are going to do is we understand what the problem is. What we want to do is we want to assign ranks to different examples, right? And now what we are going to do is to define a loss function. Let's say if you've got a given, if you think of it in terms of representation, evaluation, and optimization, we can think of a representation of a classifier or a ranking method in this case as f of x. And then the evaluation bit is where we model the problem. Here, what we are going to try to do is to define a loss function that measures ranking error or misranking errors as opposed to misclassification errors or misregression errors, right? Or errors in regression, as you can call them. So let's say you've got an example that is xi plus, and we want that example to produce a higher score because that is a higher quality apple than this other example. I'm going to call it xj negative. Let's say if you have this type of relationship, then whenever this is violated, we have an error. So let's say if you got a good quality apple like this one, I'm going to try to draw a good quality apple. We want the machine learning model to produce a higher score for this apple in comparison to, let's say, apple that is nasty. Okay. And that's whenever this is not true in our given training data set, we have a misranking. And that's what we are going to measure. So if f of x plus is greater than f of xj negative, then there is no error, right? But if this relationship does not hold for our given training examples, for which we know the quality assignment or ranking labels, we have got ourselves a misranking, and that's what's being measured over here. Here, one is simply the indicator function, and which takes in the condition, and whenever that condition is satisfied, it produces a value of 1, otherwise it produces a value of 0. Okay, so that's what this whole thing does. And if you think about this error function, it's simply comparing each example to each other example. So you've got two loops. Each example is being compared to each other example, and whenever the ranking constraints are violated, you get an error. So what we are doing over here is essentially quantifying the number of ranking errors. Just to home that point, I'm going to give an example. So let's say we've got these positive examples that you see over here, and then we've got some negative example. Let's say if this is classification, and you've got a machine learning model called F1. So this is a classifier, and what that classifier does is that it produces scores so that the highest score is for this example. So this is the number line on this axis, on the x-axis. So this is the highest score, and then you've got the lowest score for this example. And this is a threshold that we are using to classify positive from negative. So as you can see that there are two negative class examples that are below this threshold. So those are being classified correctly. There are 4 positive class examples that are above this threshold that we have chosen. So those are being classified correctly. Whereas these 2 examples over here, these should have had a negative score, but they have a positive score or a score greater than our threshold. So these 2 examples are being misclassified. So if you use the definition of classification error over here, the number of total examples is 8, and 2 out of those 8 examples are being misclassified, and that leads to a classification error of 1/4, right? So that's good. We can measure how bad the classifier 1 is on this particular data. But let's calculate what the ranking error is for this. Remember, in our ranking model, we were comparing all examples in the positive class, and we were seeing how many times are those examples ranked below a negative class example, and we were counting the number of those and dividing it by the total number of examples. So that was the formula. So we had, let's say, a positive example xi and a negative examples in j. So we had j is equal to 1 to n and I is equal to 1 to m. Okay, so let's measure that error. We have if you count the ranking error for, if you quantify the ranking error for this, we say that this negative example is being ranked below this positive example, so there is no error for this particular pair, for this pair, because this is not a violation of the ranking constraint which is there. But this negative example is being ranked higher than this positive example, so you've got one misranking there. Similarly, this negative example is being ranked higher than this positive example, so there are two misrankings. Similarly, this negative example is being ranked higher than this positive example, so there are three misrankings now, and then you've got a fourth misranking over here, right? So you've got a total of 4 misrankings out of a possible total of 4 by 4, that is 16, and that gives us a ranking error of 1 by 4. You can go ahead and verify this yourself. Okay, for classifier 2, if we calculate the ranking, the classification error, we say that there are 2 examples that are being ranked, that are being misclassified, because these should be below this threshold that we have. So you have about 2 out of 8 examples that are being misclassified. So the classification error is 1/4. However, the ranking error is larger because this negative example, there's a misranking here, there's another misranking here, because this negative example should have had a score lower than these positive examples, right? So you've got 4 misrankings due to this, and then you've got 4 misrankings due to this, resulting in a total of 8 misrankings, and then you have got a total of 16 pairs, so the resulting ranking error is 1 by 2. If you take an extreme example, let's say you've got 2 positive examples and 98 negative examples, and you do a classification error analysis on this, we can say that there's only one misclassification out of all of these 100 cases. So you've got a ranking classification error of 1/100, or 1% in this case. However, if you calculate the ranking error for this one, then we see that 98 of these examples are being ranked higher than the positive example. So there are going to be 98 misrankings, right, out of a total of all of the pairs that we can calculate, right? So there are 2 positive examples, so that is going to be 98 or 2 times 98. So this is going to give you a ranking error of 1 by 2. So I hope you understand the ranking loss function. It simply measures like what was the intended ranking. The intended ranking being that a given example should have been ranked higher than another example. So let's say your training data set is then going to comprise of all the features that are all the examples that are given to you, but also this ranking information over the training data set, that this example should be ranked higher than this example, or this example should be ranked higher than this other example, and so on. So we have defined we have quantified the ranking error, and the next thing we are going to do is going to go ahead and formulate this into a more mathematical way. So we have a representation, and what we are going to do is to formalize this loss function, or this misranking loss, and then we're going to do optimization to achieve ranking classifiers. And these ranking methods actually form the basis of various types of recommendation systems. For example, Amazon, I'm going to like this book better than this other book. Okay, so that's the sort of the practical applications of these methods. Similarly, you can think of ranking information retrieval. Let's say if you want to do Google search, what I ideally want is when I search for Warwick, the first page that is ranked at number 1 should be related to Warwick in comparison to the second page, and so on. So if the relevant page is at, let's say, rank 10, whereas irrelevant pages are at rank 1, we have got a serious misranking going on for our search engine. Okay, so unfortunately in this case, Google actually produces a very good result. The first page I want is actually related to Warwick at least. Okay, so you can use that. Similarly, ranking plays a huge role in practical chemoinformatics or bioinformatics drug design. Let's say you've got a bunch of compounds, and you want looking for a promising drug against a particular virus, say the SARS-CoV-2 virus. So what you do is you screen, let's say if you screen a bunch of those compounds for its efficacy against that particular virus, then we see that this particular compound is more effective than this other compound, and we can use this information to say to discover new compounds that are going to be more effective. So this is how ranking is used in drug discovery as well. And what we are going to do next is we're going to solve a problem called generalized instance ranking. And this has a large number of applications. Let's try to formulate this problem and then let's try to solve it using our REO principle. For solving this generalized ranking problem, what we are given is training examples as pairs, such as xi is going to be ranked higher than the corresponding other example xi dash by an amount ri. Okay? Let me give you an example of what this actually means. So let's say you've got a person or an apple. Let's take the apple example. Okay, let's call this, I want this particular apple whose feature representation I call as x1. And then I have another apple which is not of such a good quality. Okay, horrible apple drawings, but I hope you are getting the idea. So you've got a corresponding quality score for this particular apple, which is, I'm going to call this y1. And then you've got a corresponding example x2 for which you have got a quality score y2. And what I really want is I want y1, so I want f of x1, the score generated by my machine learning model for the example x1, should be larger than f of x2, and it should be larger than the difference between these two, f of x1 minus f of x2, should be at least be equal to the difference between the corresponding quality scores between them. So let's say if you give the highest quality apple a score of 5 and the lowest quality apple a score of 1, then what I essentially want is, I'm going to call this R. Okay? This is going to be the difference between the two, and that is going to be 4. That's what I essentially want. So I give you a pair of examples, and with a constraint that this example should be ranked above this other example by an amount that is given by a value R. So in this particular problem, or in generalized instance ranking, you have got pairs of examples. You can make pairs of examples. One example is x1 and the xi, and the corresponding example that is to be ranked lower than xi, in this case, is denoted by xi prime by an amount r1 in this case, or ri in general. So you've got pairs of examples and you are given a rank difference between them. If two examples, let's say if you got an example that has of cancer, for example, a particular person is at grade 3 and another person is at grade 1, then what I want is from the machine learning model to be able to learn this difference in these grades. So a higher misranking error is when the machine learning model is not able to learn the difference between grade 3 and grade 1 in comparison to when we have a grade 2 and a grade 1 cancer. Okay, so I hope that that example helps you understand this generalized instance ranking problem a bit better. So you've got these pairs of examples, you've got their rank differences. So another example can be a pair of web pages and the difference between their ranks. So let's say if I want to use machine learning to train a Google-like search engine, then I need training data. So let's say if I have given you a data set in which you have had a certain query and it produced these two different results. And what I want from you or from the machine learning model is that a particular web page that is more relevant should be ranked higher than this other page that I have, and the difference between their ranks should be at least this RI value that I've given to you. Okay. So what we want from this is we want a example to a real value. Okay. So it's a function that maps not pairs of example, but a single example, right, to a real value. It generates a real value score for that example, so that f of xi is the rank of that example, and what we want is we want f of xi minus f of xi dash to be at least ri. So if ri is so let's say if you got ri is equal to 4, then we want f of xi minus f of xi prime to be at least 4. If it isn't that way, then we have an error. So what we've done over here is we've defined the problem, we've formulated what we want, and now we are going to write our loss function or error function based on when that constraint or that ranking constraint is not satisfied. So in this case, whenever f of xi minus f of xi prime is less than the value ri, then I have an error, right? And I'm just going to rewrite this whole thing. I'm going to call it ri minus, I'm going to use f of xi prime, this will be prime, f of xi minus f of xi prime. If this thing, this expression over here is negative, that means ri is actually greater than this value, you have yourself an error. Okay? So that is how we define an error in this case. So this is simply a rewrite of that that thing. So if we move this whole beast to this place, this is what we get, and we can write it like this: is less than 0 is less than that, or in other words, ri or this whole thing is greater than 0. So whenever this case, I'm sorry, I think I misspoke earlier. Whenever this is the case, you have yourself a misranking error for this generalized ranking problem. So that's what we are going to use to build our loss function. And this is our loss function for this particular problem. I want you to pause here a minute and try to formulate this loss function yourself. I want you to be trained to design novel loss functions, because when you'll be given a new problem, you'll be you can if you can define the loss for that function, you can essentially do anything from that. So let's say if you got this f of xi and you got f of xi prime that is given to you in training data, can you show that this loss function is an effective loss function? So whenever ri minus f of xi is greater than 0, or this whole thing is greater than 0, you've got yourself a loss function, because what we really wanted is we wanted f of xi minus f of xi dash to produce a score that is ri. Okay, so that was the ranking constraint. And what we next do is simply formulate it in the form of a structural risk minimization principle. Look at this loss. That's the only change. We have got a good old regularizer over here, and we can solve this problem using any optimization technique. This can also be kernelized. Okay, we use these. I hope that you have now a good understanding of the ranking constraint. So instead of saying that I want this to be classified into this category, what we are saying is that we've got these two examples, and we want a certain ranking constraint that is given to us over the training data. We want the machine learning model to rank those ranking constraints. Okay, we use this ranking methods in identifying different anti-CRISPR proteins, and there's a whole video that I'll post on this if you want to see how this has been applied in practice. So if you, just to give you a summary, CRISPR is a technology that allows you to do gene editing. However, CRISPR has a problem in that we don't know how to stop it or what can stop it. So what we wanted to do was to discover proteins that could inhibit CRISPR technology or stop CRISPR. The development of CRISPR was done by these two scientists, Dr. Jennifer Doudna and Dr. Emmanuel Charpentier, who won last year's Nobel Prize for this invention of theirs, CRISPR, and it's a huge step forward in biology. But it had a one of the issues with it is that we want to identify proteins that enable us to stop CRISPR when we want to. So essentially giving a set of breaks to CRISPR. And we modeled it as the discovery of these anti-CRISPR proteins as a machine learning problem, because we had some examples, only 20 of them, for which we knew that these examples, these proteins actually inhibit CRISPR, and we formulated a ranking problem out of that. And what we did is we had a protein that we know is able to inhibit CRISPR better than some other proteins that were given to us as part of our training data. And we formulated a ranking problem out of it to develop ranking constraints, and that resulted in a method called A-Cranker. And we used A-Cranker to discover new proteins that can inhibit CRISPR. And we did this work together with Dr. Jennifer Doudna. So she was a co-author, and we were able to identify novel proteins. And if you want to read that, an application of that, of how these ranking constraints were made and how they were applied in practice, I welcome you to do that. If you just want to learn a little bit more about CRISPR in a very casual way, please go ahead and read this book, A Crack in Creation, which is written by Dr. Jennifer Doudna. It's an excellent read. I strongly recommend it. But the main goal I had in mind, I have in mind of asking you to read it if you want is for you to understand how we can start off with a problem in a very different domain and work your way through to design a novel machine learning method that can solve a problem and give you some novel insights or discover something new. Ranking methods or ranking constraints are a different way of what we've been doing earlier using classifiers, that is learning from data. So if you're given a machine learning problem, think about it, whether it's a regression problem, whether it's a classification problem, whether it's a ranking problem, and then choose the appropriate method that you want to apply. However, more general than that is the fact that you should try to formalize loss functions for a given problem by understanding the problem itself. Once you write the loss functions, you are good to go. There are methods, if you have a representation and if you have an evaluation, you can use those to solve problems in a completely or almost completely automatic manner, just like I had given you a tutorial of doing that in PyTorch. Okay, and these ranking methods are used in recommender systems, just like we're going to see. So please try to understand this particular loss function that lies at the core of this particular problem and how it can be used in practice. Thank you.